right? It's outside the set. So a convex set is one which, if you take any 2 points in the set, the line segment connecting those 2 points is in the set.
So it is literally like the convex definition, the graphs of like
Well, I guess.
I mean, like geometrically speaking.
Wow, I'm getting worse. So, oh, that one works. Okay. The convex hull. So you can look at so-called convex combinations of points. So if I have P1, P2, pk, its convex combination would be something like this: T1, P1 plus T2, P2 plus plus Tk, Pk, right? This set such that what? Exactly, yeah. And also 0 less than or equal to Ti less than or equal to 1 for all I. So these coefficients are taken from the unit interval. That's called the convex combination of points. The convex, so if this is actually an example, what this is, as it turns out, is the convex hull of the set containing these points. Now that's an exercise. I'm sorry?
Is that
TKPK. TKPK. So just to give you some simple examples, if I have 2 points, say P1 and P2, what's the convex hull of the set containing those 2 points? Right. If I have 3 points, what's the convex hull of the set containing those 3 points? Yeah, it's the triangle. It's the filled-in triangle. Times like this, I really wish I had a chalkboard, because doing this just doesn't do it justice. The point is, you can reach, how do you get these different, like P1, for example, is P1 plus 0 P2 plus 0 P3. P3 is 0 P1 plus 0 P2 plus 1 P3, and so forth. And everything else in here you find between. I use this idea of convex hull when I describe in Calculus 3 how to parameterize a parallelogram given a set of points. I just let parameters range from 0 to 1, basically, right? Like, remember this? I don't know, maybe you see it, maybe you didn't, but if I have a vector A and if I have vector B like this, then to get this parallelogram, I just do something like, x of uv is equal to the base point, whatever that is, plus u times a plus v times b. And that's for 0 less than or equal to u comma v less than or equal to 1. If you look at what I'm doing, I'm really taking the convex. I mean, the idea behind this is the convex hull. Okay, so if I have like 4 points, then it's like, that's the convex hull, right? Now he points out if you had something like this, then the convex hull would just fill in this piece that you're missing, right? Okay, enough about that. Now, what's a polytope? A polytope is the convex hull of some finite set of points. I've been showing you polytopes. All right. Now he defines an affine hyperplane. What's an affine hyperplane? Basically, it's just half spaces in Rn, right? So in n equals to 1, it's kind of boring. It's basically just raised like this. Or, well, no, what's wrong? Affine hyperplane. How does he define it? Oh man, guys, help me out here. Yeah. What you just told me, x and Rn such that what? G of x comma v is equal to a. For some v and a in Rn, right? Oh, sorry, v and Rn and a and r, right? So if you think about n equals to 1, what is that? So you pick a point, v. And then you pick an x. And what is the condition? G of x comma v is equal to some constant a, right? This is the metric, so I believe he means that that's, positive. But basically what you're looking at then is that this distance is a, right? So, Well, I mean, I know I'm having a little bit of trouble here seeing it, but I know that in the one dimension, the affine hyperplanes are just points. In n equals 2, the affine hyperplanes are something like, they're lines, right?
Wouldn't it be 2 points?
That's what I'm wondering, but I don't think so. Oh. I mean, it says any set of the form blah is called an affine hyperplane. It determines 2 closed half spaces. I mean, so when I think hyperplane, okay, you know what? I don't know what's wrong with me. I mean, I know what the answer should be. I just can't quite connect it to his silly definition at the moment. So, again, for n equals 1, it's just a point. For n equals 2, the reason for affine is just that it doesn't have to be a line through the origin. It can be any old line. For n equals to 3, you're looking at, planes for your affine hyperplanes, right? N equals 4, it's a 3-dimensional space. The point is these affine hyperplanes divide the ambient Rn into 2 pieces, above and below, one side or the other. Let me just work it out. I'm sorry, guys. Let me pick on 2 dimensions for just a second. Well, I mean, if this is, I guess the question is metric. Nathan, is he using metric in the sense of metric or in the sense of metric?
Well, he says using the usual Euclidean metric.
That doesn't help us.
I think earlier in the book, though, he uses like g of dot comma dot. It's like not.
So what is g of what is g of x comma v? What's that equal to? Whatever it's equal to, it has to give us these as the affine hyperplanes. That much is obvious from the rest of his section that that's what he means by it.
Earlier in the book, in chapter 1,
G
of u comma v.
is u dot v.
Yeah.
So this is x dot v. Oh, okay.
So it's an inner product, not a metric.
Okay. Well, he says Euclidean metric, but isn't Euclidean metric the same as an inner product?
Metric and inner product are used interchangeably in different parts of math, yes. I mean,
Yeah, he used
but at the same time, it's not a distance function, right? It's not a distance function.
No.
If we think of distance function, we get 2 points, like you were saying, Nathan. I agree with that. Okay, anyway, let me move past this. And he's got these great pictures, right, where he shows you how a polytope can be seen as kind of being, kind of squeezed between these supporting hyperplanes, right? So, and then he has more definitions here. For example, any set which is formed from a polytope intersected with one of these affine hyperplanes is called a what? It's called a face of P, right? So this definition allows for the face equal to P. All other faces are proper. The dimension of a face is the dimension of the smallest affine subspace containing it. A zero-dimensional face is a vertex. A one-dimensional face is an edge. An n-minus one-dimensional face is a how do you say that? Ambient French student. Facet? Okay. It's not like facet or something? Okay. I don't know. Facet.
A facet is like the face of a gem. If you're talking about the gem that
Oh, right.
12 facets, it's 12 faces.
Ah, very good, very good. So like the face of a gem? Okay. Very good, very good. The collection of all facets of a polytope is the boundary of the polytope, and the interior of the polytope is, if you remove the boundary, then you have the interior. Because polytopes have facets or seats, they're also called polyhedra, which means many seats.
I think we don't know that.
What's that?
I think we don't know what poly.
Yeah.
I mean, come on, we're not English students. The things they explain and the things they don't.
Yeah, it is.
I know, yeah, it's like, what's their reasoning behind telling us stuff, like repeating stuff we already know and only saying the things we don't know?
So, oh man, son of a motherless goat. Let's see here.
Oh wait, no, that's not opposite.
So what? And you don't specify it as a goat for that one.
Well, I don't feel too bad. I knew it was a little bit ambitious to think I could cover chapter 4 and 5 in a day. I knew that was like a little bit ambitious. I will tell you what we're going to do next is we go on to describe what's called homology theory. All right. So basically, what we're going to do is keep studying these things. We'll study how you can basically build this operator which takes you from like sort of like the triangle to its edges, so-called boundary operator. And then you find ways of there's an algebra you can build on these polytopes and somewhat analogous to the exterior derivative. And this ends up defining something called homology over a space, which is based on triangulating the space. Then the homology groups are, in some sense, dual to the cohomology groups, as we'll see. But this is all necessary because this is what underlies the setup of integration over a manifold. And that's really the reason I was attracted to this book, is because it connects the deeper theory of integration at least a little bit with this larger discussion of topology, which I think is really great. Before I go, though, today, I should read you. Yeah. Before I forget, though, we should enjoy this story together. When I was a schoolboy, I was seized by the idea that everyone has an invisible tail at his back. This tail is very light, 1,000,000 miles long and very thin. The trails behind as we walk, from birth to death. The tail extends far away beyond our world and originates in the land of the dead. When we walk, the tail is reeled out from its source, and when we've pulled out the entire tail, we die. The strategy for a long life, therefore, is to try to avoid pulling out your tail. In order to do this, walk null homotopic paths as much as is possible. When you return, follow the same route, never go through a tunnel. My ideal world was a universal covering space of the real world, if there is such a thing. My ideas completely obsessed me. I was trapped by my own fantasy. I even came to loathe people who crossed my path behind me. Hopefully next time we will understand this a little bit more.
So math just happened.
This is from Galois' Dream. Group Theory and Differential Equations by Mikhail Kuga.